So we'll start the zeta potential part today. So zeta potential basically the surface charge, as I mentioned, surface charge of the colloid particle. Okay. Determination. So in your syllabus, so how the zeta potential is being um, quantified from the electrokinetic phenomena, as I taught you before, the electrophoresis or the electroosmosis, and even from the streaming potential that you need for the numerical problems. Okay, so zeta potential, as I mentioned, it is the surface charge of the colloid, so it is all related with the charge of the colloid surfaces. Okay, so so it is at the basically surface of the shear, so it is related with the surface of the shear. Okay, but the particle relative velocity, but the relative velocity between the particle and the fluid is said to be zero at the surface for the zeta potential calculations. So from the electrophoresis, let us consider a spherical colloid particle is moving. So determination, first what we will do, first we will do determination of zeta potential, from electrophoresis. Okay, so these processes I already taught you before. So let us consider a spherical colloid particle. A spherical colloid particle is moving with a velocity u. Okay, and in an applied electrical field, that is E. Okay, so a colloid particle is moving with a, you can write it down. A colloid particle is moving with a velocity u, and in an applied electrical field, that is E. So the electrophoretic mobility, what is electrophoretic mobility? So that is the electrophoretic mobility is equal to u by E. Okay, so u by E, sorry, u by E is given by 2 epsilon 0 zeta by 3 mu. I'll be coming to that, but kappa rs is less than equal to 1. This already you know, this is Huckel equation.
Sir, can you repeat the symbols used?
Which one? Which one?
Sir, electrophoretic mobility is equal to U by E, and then the next line, U by.
That is the electrophoretic mobility is equal to 2 epsilon 0 zeta by 3 mu. Okay,
So that is the value of U by E.
u by E. That is the value of u. Oh, it is not saying that. That is the value of u by E. Okay, that is
Yes, sir.
that
Yes,
is
sir.
that is called Huckel equation. It is valid when kappa rs is less than equal to 0.1. Okay, similarly u by E, the mobility, oh, why it is happening like this, u by E again is epsilon 0 theta by mu when kappa rs is greater than 100. Okay, this is called Smoluchki's equation. From the electrophoretic consideration of electrophoretic mobility, this two is equation is being, I'm not going into details of the this thing, the equation, how to develop these things. You just remember these things. The u by E is equal to 2 epsilon 0 zeta by 3 mu for kappa rs is less than equal to 0.1. This is called Huckel equation. And similar, when kappa rs is greater than 1, it is called as Smoluchki equation. Smoluchki.
Sir, what is mu?
Which one?
So mu is viscosity, sir.
Yeah, it is viscosity.
Yes, sir.
It is viscosity. Okay. And kappa, already in from the stern layer I have heard what is the kappa. Kappa mone porche, what is kappa? Debye Huckel parameter, kappa. Last class I already mentioned the kappa. So kappa, this is when kappa RS is greater than equal to 100 and when it is less than 0.1, when the salt concentration is very high, when the salt concentration is very high, then kappa RS will be greater than 100. Then you consider this
মনে
equation.
পড়ছে না।
আগের দিনে ক্লাস না করলে মনে পড়বে না। আগের দিনে ক্লাস করেছিলে? আগের দিনে ক্লাস না করলে স্টার্ন লেয়ার আমি পুরো করিয়ে দিয়েছি আগের দিন। ডিবাই হুকেল প্যারামিটার,
Yes, sir.
ডিবাই লেংথ, so that is the ডিবাই হুকেল parameter. So this is kappa RS is greater less than 0.1. Kappa RS পুরো denote করছে why, how the, it again depends on the salt concentration. If salt concentration is very high, then kappa RS will be greater than 100. Then this equation valid, Smolowski equation. When salt concentration is low, then kappa RS is less than 0.1. Then Huckel equation valid. So you have to calculate the zeta potential using Huckel equation when the salt concentration is high, low, and you have to consider the Smolowski equation when the salt concentration is very high. So you have to determine the salt concentration using this one, verify it whether it is very low or very high, then accordingly you utilize the equation which is required. And this is permittivity, and permittivity is vacuum, zeta potential, and this is the viscosity. All you know, okay? So this is from electrophoresis. Similarly, you have to do from electroosmosis. Okay? Determination of zeta potential from electroosmosis. So how? So this is one equation is zeta potential is equal to V mu f 0 E A. এটা ইটা এরকম লিখতে কি এরকম হচ্ছে কেন? E A. Okay? V, what is V? V is the volumetric flow rate. Okay? Steady state volumetric flow rate in a capillary which is due to the electroosmosis. And RC is the radius of that capillary. RC is the radius of that capillary. So again, you have to find out KRC when it is greater than, if you find it is greater than 1, then only you can find out this is zeta potential from the for osmosis. Okay, so this streaming potential is out of the syllabus, so you can calculate the zeta potential using these three equations from electrophoresis and electroosmosis respectively. So only numerical problems will come from that. As I mentioned in the previous classes, so there are few terminology which you need to understand. So that is called, first is তোমরা এগুলো লিখে নিতে পারো, আমি পরে নোট দিয়ে দেব তোমাদের যদি বানাতে পারি, এখন আমার কাছে নোট রেডি নেই, আদারওয়াইজ আমি বলছি তোমরা লিখে নাও। Hofmeister series. So what is Hofmeister series? Do you know what is lyophilic sol and lyophobic sol? Lyophilic, what do you mean by lyophilic?
Sir, is it possible to go back to the last page once more? Sir, something just had to write something.
Okay. This one?
Yes, sir. Yes, sir. Thank you, sir. I've taken the screenshot.
This is zeta potential V, viscosity mu, epsilon 0, E A. Okay, and KRC should be greater than equal to 1. So Hofmeister series, what is Hofmeister series? What is lyophilic salt? Lyophilic salt is water loving salt. So first Lyo Hofmeister series. There is a series named after the name of scientist Hofmeister. So lyophilic lyophilic salt means a salt which loves water. So lyophilic salt. So now let's say let's say small amount of electrolyte has been added to lyophilic salt. Very small quantity of electrolyte. Let's say potassium chloride add করা হলো lyophilic salt এর মধ্যে. Small amount of electrolyte. What will happen? So Hofmeister series is being determined by considering the variation of zeta potential, taking the lyophilic salt, and when addition of how the addition of electrolyte changes this property in terms of zeta potential, in terms of its surface charge, that is being governed by a particular series of the cations or what. I will be coming to that. So when a small amount of electrolyte has been added to the lyophilic salt, so what I am suggesting to addition of small amount of electrolyte, then addition of high amount of electrolyte. What will happen to that lyophilic salt? So when the small amount of electrolyte has been added to the lyophilic salt, its zeta potential completely diminished. So the lyophilic salt becomes almost uncharged in nature. Is zeta potential is completely diminished, but when did this zeta potential, why? Let's see. It's okay. Colloid particles. It's a colloid particles. Okay, these are colloid particles. Basically, the colloid particles, they are all are negatively charged. Okay, now in the solution you have a part of colloid, huge number of colloid particles. Why the coalescence occur? When I talk about the coagulation or the coalescence, okay, why the coagulation occurs? This particle comes in close contact with each other and form aggregates. Due to van der Waals force of interaction, these particles, these colloid particles, comes close to each other when it is uncharged. When it is uncharged, come close to each other and form aggregates, right? When it is uncharged. Now I'm talking about the particles are being charged. So particle, when it is charged, it is all surfaces are negatively charged. So as the surfaces are negatively charged in the solution, what they will do? They will come to each other, or they will repel each other?
Repel each other.
They will repel each other due to the same charge, right? So when zeta potential exists, they will repel each other. Now ebar dhoro, now you want to separate these particles out from the solution. So you filter these things out, right or wrong? So right or wrong, please communicate with me. If in a solution, let's say you have a these colloid particles, charged colloid particles are there. So in order to separate this one, you need to filter these things out using a media filter, whatever, right?
Yes, sir.
But as it is separated by the charge, whether the filtration will be so easy.
Because the colloid particles are small, you think that they are existing separately, it will be difficult.
They are existing separately. So in the bulk medium, the one particle will be here and one particle will be here. They will be far apart.
Yes.
So filtration by the normal process becomes very difficult because they're far apart. So in order to pull them to each other, so you need the aggregates of the colloid polymer. Then only you can filter these things out easily. So what you need to do, you need to neutralize the charges, right?
Sir, sir,
হ্যাঁ বলো।
sir, some students are waiting in lobby. Please enter them. They're asking to give them entry.
ক্লাসের মাঝখানে এগুলো হলে ওকে। সো হোয়াট আমি কি বলছিলাম? Okay, now these particle, if the charge particle, negatively charged particle, due to that charge, same dipole repulsion, they tend to stay far apart from each other. But in order to separation proceed to facilitate, in order to proceed further, in order to take that filter that colloid materials out, why do you need to filter that one? Your question should be that, sir, আমাদের ফিল্টার কেন করতে হবে? বিকজ যদি তুমি ওয়াটার নাও, যে কোনো ওয়াটার ট্রিটমেন্ট করো, যে কোনো ওয়াটার ট্রিটমেন্ট, সো দিজ আর ইম্পিউরিটিস। সো ইন অর্ডার টু চেক দ্য ইম্পিউরিটিস, ইন অর্ডার টু টেক দ্য ইম্পিউরিটিস আউট, ইম্পিউরিটিস কিভাবে বের করা হয় দেখো, আমি তোমাকে বলছি। সো দিজ আর নেগেটিভলি চার্জ। আমি কিভাবে বললাম দিজ আর নেগেটিভলি চার্জ? দে স্টে অ্যাপার্ট ফ্রম ইচ আদার। Now your wastewater contains the cations of irons or aluminum or zinc, etc. Right? Right or wrong? Or lead?
Yes, sir.
Or lead or arsenic, whatever. These are
Sir,
the
sir, you said that the colloids are usually negatively charged, but so why is that?
it is inherent that they form the electronic cloud among মানে on top of that. স্টার্নলের আগের দিনে ক্লাস করেছো?
Yes, sir. Yes, sir.
So that is due to that diffuse layer formation. They are negatively charged, colloid particle negatively charged, and due to that double diffuse layer, they always they form a negative atmosphere among itself, always negatively charged, cloud of electrons. Due to the presence of cloud of electrons, they always negatively charged, এইরকম ভাবে থেকে যায়। So in order to neutralize the charge, তোমাকে কি করতে হবে? In order to neutralize the charge, you have to somehow এর মাঝখানে পজিটিভ আয়ন ঢোকাতে হবে, right?
Yes, sir.
For charge neutralization, পজিটিভ আয়ন ঢোকাতে হবে কিনা, ফলে চার্জ নিউট্রালাইজ হয়ে যাবে। Once the charge is being neutralized, they can form the coagulants and we can easily filter that things out. Abundant source of electron cloud, that is why it is negatively charged. And now এইখানে যে ওয়েস্ট ওয়াটারে কি থাকে, ওয়াটারে কি থাকে, এই সব ক্যাটায়ন গুলো ঘুরতে থাকে, রাইট কি রং? these are pollutants.
Yes, sir.
এইগুলো কি করে, এর মাঝখানে ঢুকে পড়ে, মাঝখানে ঢুকে কি করে দেয়? So you have negative positive negative positive negative positive atmosphere. So these are neutral, becomes neutral, from negatively charged becomes neutral, and then comes the van der Waals force of attraction or interaction. Okay, then comes that, and they comes close to each other. They come close to each other, these particles, due to this charge neutralization. So basically in this whole these are these, and in between there are metal cations of +2 or +3 entrapped. বোঝা গেল? That metal cations from the wastewater, they have been entrapped in between the colloid, negatively charged colloid particles, and the charge has been neutralized, and they can be filtered out. So filter যখন করলাম, আমরা কি করে দিলাম? ওয়েস্ট ওয়াটার থেকে কি বের করে দিলাম?
So the colloid suspension.
Metal particle গুলো বেরিয়ে গেল, though that the metal particle which are the in the wastewater that can be eliminated out by the filtration now using that method. বুঝতে পারা গেল? আরেকবার বলবো কি বললাম? Or you understood? As it is negatively charged, so simple filtration method is not enough, is not possible. You cannot filter these things out because they tend to, as the charged particles tend to run away from each other because of the same charge. Because of the same charge, they tend to run away from each other. As it is running away from each other, what do? We need to do? You need to hold these materials together in order to filter these things out. So in order to hold these things material, you need to neutralize the charges. So how to do that? How to do neutralize the charges? What to do? So you need to add some other coagulant in the system, other method, other positively charged electron, positively charged metal in the system, positively charged anion, any species which can neutralize the charge. আমি ওয়েস্ট ওয়াটার কেন বললাম? তখন এই কলয়েডাল পার্টিকেলের মধ্যে যদি ওয়েস্ট ওয়াটার দিয়ে স্ট্রিম করো আন্ডার ইলেকট্রিক্যাল ফিল্ড, ওরা কি করবে? এই পজিটিভলি চার্জ মেটালগুলো দে ফাইন্ড এ স্পেস ইন দ্য নেগেটিভ, কি হবে? তারা অ্যাট্রাক্ট হয়ে যাবে তো নেগেটিভলি চার্জ কলয়েড পার্টিকেল দিয়ে, and they find a space in between. In the process, what is happening? Charge, not only the charge is being neutralized, also that they are capturing the metal particle which are impurity present in the wastewater stream. Which are, these are the heavy metals. They take away the heavy metals. Now you can filter the things out. You get the clean water. You get the clean water free from any heavy metal. This process is done under electrical field, and the process is known as electrocoagulation. It's a formation of coagulates under electrical field. This is a very important method to remove for this in membrane technology in the separation of heavy metal from the wastewater. Using this method, it can be removed, the colloidal salts, the lyophilic salts. Again, a small amount of electrolyte, what is induced? That electrolyte, that is KCl nile K plus or NaCl nile Na plus, that is being induced in the system by this way. When it is being added to the lyophilic salt, the zeta potential is diminished. Why diminished? The charge is being neutralized by this way. বোঝা গেল এতক্ষণ ধরে যেটা বলছিলাম? Understood? Fine. So when small amount of electrolyte has been added with the lyophilic salt, so zeta potential is diminished. But the beauty of that, in this case Hofmeister series, I already told, in the electrocoagulation, coagulation takes place. But over here, when amount of electrolyte is very small, very minute quantity, the zeta potential is diminished, but coagulation does not occur. Coagulation does not occur. But when the amount of electrolyte is over a critical concentration, has been added with the lyophilic salt, that is the quantity of electrolyte is a little bit higher, so higher amount of electrolyte is being added with the salts. What happens? The dispersed substance precipitates, and this process is called salt out. So do you know? So if I write a short note on salt out, this is the thing. When high amount of electrolyte has been added with the lyophilic salts, not only zeta potential diminished, but also the dispersed substance, that is the electrolyte, is being precipitates, and the process is known as salt out. Okay. So reason, what is the reason behind salting out? If I ask you, what is the reason behind salting out? So large amount of electrolyte, it basically what why it happened? Why happened? The large amount of electrolyte dehydrates the particle. It dehydrates the particle. It could not sustain. If the particle is hydrated, it tends to float on the top of the sol. But when it is dehydrated completely, it exhausted and comes out. And the process is called salting out. Process is called salting out. Sometimes it is called co-curvation. Co-curvation. So this is why. What is the reason behind that? As I mentioned, when the large amount of electrolyte added, it dehydrates the particle. Okay. What it does, the salting out produces a liquid aggregate, not the solid. It produces a liquid aggregate. ওকে, দেখবে তোমার সামথিং কিছু ভিসকাস ড্রপের মতো, মানে এটা সলিড অ্যাগ্রিগেট নয়, লিকুইড অ্যাগ্রিগেট ফর্ম করে নেয়। চোখের জল যখন শুকিয়ে একটু একটু জেল টাইপ হয়ে যায়, দোজ কাইন্ড অফ থিংস হ্যাভ বিন ফর্ম, লিকুইড অ্যাগ্রিগেটস। ওকে, sometimes is known as viscous drop. Okay, and the process is known as salting out or co-curvation. Okay, and that those liquid droplets is known as co-curvates. Liquid droplets is known as co-curvates. Now this is co-curvation, this is salting out. When the salting out occurs, I already mentioned. Now this salting out or co-curvation depends upon the nature of the ions you are adding.
Sir, when the amount of electrolyte is below the critical concentration, there is no salting out. There is only the reduction in the zeta potential, but no precipitation occurs. But when that exceeds the critical concentration of the electrolyte, then there is a precipitation that is occurring. That is the phenomenon you just mentioned earlier.
Yes, that is salting out. You are absolutely right.
Sir,
Okay.
so sir, what is Hofmeister series, sir? How is it related?
I'm coming to that. How it is related with the salting out, I'm coming to that Hofmeister series. Until that is, it is fine. Salting
Yes,
out depends upon the nature of the ions. That salting out or co-curvation depends on the nature of the ions. A series has been created reflecting their ability to salt out. That is called Hofmeister series. Understood? Salting out depends on the nature of the ions. A series has been created. কি অ্যাড করছো তোমরা? ইলেকট্রোলাইট অ্যাড করছো, হায়ার অ্যামাউন্ট অফ ইলেকট্রোলাইট। দ্যাট ইলেকট্রোলাইট, দ্য নেচার অফ দ্য ক্যাটায়ন্স determines whether salting out will be occurring or not, and if it is occurring, how it is occurring. The selectivity of the salting out is being governed by the Hofmeister series. Okay, the salting out depends on the nature of the ions. A series has been created reflecting their ability to salt out. The series is called Hofmeister series. For cations, Mg plus 2 greater than calcium, greater than strontium, greater than barium, greater than lithium, greater than sodium, and greater than potassium. This is for cations. This is for cations. Hofmeister series is valid. So একটা তুমি MgCl2 add করছো, MgCl2 will be better chance, will have a better chance to facilitate the salting out instead of potassium chloride. So this is Hofmeister series. Process of salting out is fine. The how the anions or cations are facilitating the salting out, এখানে KCl add করছো, this chloride has also an effect on the salting out. So anions, sulfate, chloride, nitrate, and iodide. So this is the order. These are the order of salting out, preference of salting out, and the series is called Hofmeister series. So Hofmeister series bolte gele you need to understand what is salting out, how the salting out occurs, why it is occurs, and how the Hofmeister series is facilitating the salting out. So this is all Hofmeister series and co-curvation and salting out. Understood?
Yes, sir.
Next is electroviscous effect. Electroviscous effect. What is electroviscous effect? Again, it is related with lyophilic and lyophobic sol. So lyophilic sol, lyosol is higher viscosity than lyophobic sol. Lyophilic sol is having significantly higher viscosity than the lyophobic one. If I ask you why the lyophilic sol is having significantly higher viscosity than the lyophobic one, this is due to why lyophilic sol having higher viscosity in the lyophobic sol. This is due to the extensive solvation of the disperses particle. Extensive solvation, due to extensive solvation. I have not talked about the zeta potential yet. This is due to the extensive solvation of the dispersed phase particle. Extensive solvation only কি হবে? If extensive solvation occurs, then which go on to increase the resistance to flow. So resistance to flow, if it is resistance to flow is increasing, so viscosity will be increased. So that is why, due to extensive solvation, the viscosity of the lyophilic sol is higher than the lyophobic sol. Now, if you add again a small amount of electrolyte to the lyophilic sol, if you add a small amount of electrolyte again to the lyophilic sol, what happens? The lyophilic sol viscosity reduced drastically reduce the lyophilic sol viscosity instantly. Okay, let's say potassium chloride add kora holo. Okay, agar solution agar solution is a lyophilic sol. Agar solution is a lyophilic sol. Again, you add potassium chloride, let's say 1 mole per meter cube. So 1 mole per meter cube is very less amount of quantity is being added to the agar solution. Okay, viscosity around 30% decrease করে instantly by addition such a small amount of potassium chloride itself. Okay, what is the reason behind that? So extensive solvation which go on to increase the resistance of flow is not holding good over here. Okay, why? Now you are considering the formation of the electrostatic double layer over here. So decrease in viscosity can be summarized by the formation of electrostatic double layer surrounding the colloid particle. Okay, this small amount of potassium chloride or electrolyte, you may tell, the small amount of electrolyte cannot appreciably affect the solvation of the particle. Okay, so therefore here not the solvation but the zeta potential is the governing factor. So process is and the electrostatic double layer formation is the cause of reduction in viscosity, and the effect is called electroviscous effect. Okay, the role of electrical charge on the particles towards the viscosity decrement of the sol is known as electroviscous effect. Okay, আচ্ছা আমি ইয়ে তো পড়িয়ে দিয়েছিলাম the Mark-Having equation and all, আগের দিন পড়িয়ে দিয়েছিলাম। Mark-Having তো করানো হয়েছিল। Let me check the previous class. Double layer done. Oh yeah, marking is also being done. So this is Hofmeister series electroviscous effect. Okay. Next, what I'll do, I'll move on to the most important part. সারফেক্টেন্ট শুরু করা হয়েছিল?
Sir, the decrement in viscosity is electroviscous effect.
What?
Sir, the decrement in the viscosity when I'm adding electrolyte, that is called electroviscous effect. That is in lyophilic sol, the decrement that is occurring.
হ্যাঁ,
Okay, sir.
different decrement in the viscosity. At that time, the solvation effect does not hold good. The zeta potential comes into play. At that time, when you add a very little amount of electrolyte onto the lyophilic salt, your extensive solvation does not hold good. That's why viscosity has been decrement due to the formation of electrostatic double layer. So now the reason is not the extensive solvation. Now the reason for viscosity decrement, increment in viscosity is due to the excessive solvation, but here the decrement in the viscosity is due to the formation of electrostatic double layer. The
Okay.
effect is called zeta potential. Okay, সারফেক্টেন্ট পড়ানো হয়েছিল তোমাদের? Anybody সারফেক্টেন্ট? প্যাকিং প্যারামিটার? প্যাকিং প্যারামিটার সারফেক্টেন্ট পড়ানো হয়েছিল? ওকে, চলো সারফেক্টেন্টটা পড়িয়ে দিই আগে। নেক্সট ডে তাহলে সারফেস টেনশন ইন্টারফেসিয়াল টেনশনটা করব। মনে হচ্ছে আমার সারফেক্টেন্ট পড়ানো হয়েছিল, বাট নোবডি ইজ রেসপন্ডিং। আই ডোন্ট নো am I repeating or not. Okay, surfactants. I think I'm repeating once again. Nobody is following the class. That's the problem. The surfactant, types of surfactant is nothing but that the soap molecule you are adding in the water. Those are surfactant basically. Those are the sodium salt or dodecyl benzene sulfonate, SDBS. SDBS is typical surfactant. Okay, SDS. These are surfactant. This addition of surfactant change the surface tension of the water. Okay, how the surface property is being manipulated, and the mishel is being formed. Mishel is being formed by adding surfactant. What is mishel? Anybody can anybody answer? What is mishel? How the surfactant looks like? Surfactant has a head along with the tail. Okay, and these two part is surfactant. Head is hydrophilic head. This head is hydrophilic, and tail is hydrophobic. Okay. Okay, অনেকে দেখবে শীতকালে তোমরা গ্লিসারিন সোপ ইউজ করো, রাইট? হ্যাভ ইউ সিন দ্য গ্লিসারিন সোপস?
Yes, sir.
So glycerin soap hoy আর একটা ধরো Lux, you are using Lux, and if you use the Lux, you can see the Lux or any kind of soap over here, you can see the amount of froth created is very high in case of these normal soap, but in the case of glycerin soap, the amount of froth created is very less, right? কম ফেনা হয় গ্লিসারিন সোপে, but in case of these soaps, these are very অনেক ফেনা হয়। তোমার এই গুঁড়ো সাবান দাও জলে, দেখবে অনেক সঙ্গে সঙ্গে গুলে যায়। Okay, so solubility of this kind of soaps is higher, and the solubility of the glycerin soaps are lower, isn't it? Right or wrong?
Right, sir.
Okay, why this is? This again governed by this hydrophobic tail. In the glycerin, you have the hydrophobic tail very high. N is greater than 30. But in case of these kind of soaps, the hydrophobic tail is less than 10. So it readily so hydrophilicity is higher in case of these soaps, but hydrophilicity is lower in case of glycerin because the number of hydrophobic chain is high. So that's why it hardly dissolves in water, but these are readily soluble in water. These are the surf Okay, so these are the surfactant having hydrophilic head and hydrophobic tail. Okay, now how the micelle is being formed? This is called micelle. This, okay, this is called micelle. Reverse micelle can also be formed. Reverse micelle can also be formed. This is called reverse micelle. When the concentration of the surfactant goes beyond the limit, then the micelle as being reversed, the and form reverse micelles. তোমরা মিশেল সম্পর্কে পড়োনি আগে? Don't you know what is Michel?
Yes, sir. We have studied in school in our like 11th and 12th we have studied in chemistry.
Yeah. So these are the Michels. So hydrophilic tail and hydrophilic head and hydrophilic tail, they forms the Michel. The surfactant forms the Michel. Once the CMC equal Michel concentration is, this is the governing factor. When it is crossed, there is huge difference in the surfactant of the surface tension of the so properties have been altered when the CMC is being crossed. Okay, so I'll be coming to that. So Michel is having hydrophilic head with the hydrophilic tail in between. Okay, so hydrophobic. So types of Michel are, first are anionic, cationic, zwitterionic, and 4 is non-ionic. Okay, most industrial used Michel are anionic Michel. Most industrially used Michels are anionic Michels. Okay, soaps, anionic Michels. Okay, this is the structure. Soaps are all anionic Michels. All soaps anionic Michels. Number 2, what I told, cationic one. Okay, where use ore flotation. Have you heard about the froth flotation technique? How many of you? Froth flotation. How many of you heard about that? Froth flotation technique or ore flotation technique? These are another property, very poor detergency. Detergent power very poor and very high cost. Froth flotation, জানো কেউ কিছু?
No, sir.
Let's say you have just understand. I'm not in detail, in short. You understand a mixture of hydrophilic and a hydrophobic material. Mixture, hydrophilic one and hydrophobic one. You have calcium carbonate, you have barite. Okay, so mixture of those two solid particles. So you need to separate the things out. How do you separate the things? You have a hydrophilic part, you have a hydrophobic part. How to separate the things? Mix all together. So what, first step, you add water. Once you make the slurry of water, what will happen? The hydrophilic part will go into the solution with the water. ঠিক আছে, hydrophilic part will be soluble in water and hydrophobic part will insoluble, will be staying as such, right? Now you filter the hydrophilic part out. Now due to now you filter the hydrophilic part out and you have the hydrophobic part. এবার হচ্ছে metal recovery, the ore flotation. The ore will be attached, the ore I am talking about, the flotation will be attached with the hydrophobic one. The ore is attached with the hydrophobic one. Hydrophilic part আমি বের করে দিলাম, hydrophobic one. Now the ore flotation is the process of taking that precious salt, precious metal out from the hydrophobic part. How to take that precious salt out from the hydrophilic part is called ore flotation. First, what we'll do, we will make this make a water slurry so that all the hydrophilic moiety will goes into the solution, and the hydrophobic part where the main ore is attached is being left behind. That hydrophobic part, you add the cationic surfactant into that. Cationic surfactant. What cationic surfactant does, it further separates the hydrophilic and hydrophobic part out, and it helps to move, and in a separate, from a separate unit, air condenser diye ki kora hoy, air is being passed. So air is also hydrophobic, so that cationic part will be attached with the air, and that anionic cationic part, cationic metal I'm talking about, is attached with the air because air is also hydrophobic in nature. What this cationic surfactant does, it not only removes all the hydrophobic part from the hydrophilic one, but also promotes this adduct on top of the solution, so that you take the flotation, take the ore out very easily. There are other technical specification on which I am not going into details of that. It will entirely mechanical operations thing. There is a course in chemical engineering where this is being taught. Also lab is there. So this is the ore flotation by which you take the precious metal out. In that section you use the cationic surfactant, but in industry you hardly use those things. Industry you use the anionic surfactant one. Okay, so the cationic surfactant hardly being used due to its high cost and poor detergency. Okay, third is Zwitter ionic. All the cosmetic industry, in all the cosmetic industry, the Zwitter ionic surfactant is being used. Cosmetic industry. The Zwitter ionic surfactant is being used. What is the structure of Zwitter ionic substance? This is RNH2 plus CH2COO minus. Okay, long chain fatty acid. These are long chain fatty acids are the Zwitter ionic surfactant. The main, as it is being used in cosmetic industry, the beauty of that is it is less irritating to eye. It is not irritating to eye. These two are irritating to eye. সাবান মুখ চোখে দিলে চোখ জ্বলে না, that is why due to that. But the Zwitter ionic surfactant cosmetic তো চোখে দাও চোখ জ্বলে না, because it is less irritating to eye. The long chain fatty acids are not irritating to eye, but these are irritating to eye. That is why Zwitter ionic surfactant is being very widely used in cosmetic industry. Okay. Fourth and but not the last is non-ionic. What non-ionic? Non-ionic, it is being associated with the production of foam. It is associated with the production of foams. Okay, used in emulsion, paint industry, also in cosmetic industry, but basically for men's cosmetic, that is the shaving gel and all, non-ionic surfactant has been used, and also huge application in paint industry, non-ionic surfactant. Okay, there is another class of surfactant which is not important, that is the Gemini surfactant. Ladder kind of structure is there, which is very complicated, so I'm not going details of that. Okay, you write it down, or you can record it also. So these 4 types of surfactants are there. Now as I already mentioned, how the Michel is formed. So there is a boundary called critical Michel concentration. Okay, and the uh, let's say this is concentration of surfactant. So once the concentration of surfactant is very high, is cross the critical Michel concentration, then what happened? Reverse Michels are formed. Okay, so this is the critical point. Until that, Michels hold good. After that, reverse Michels is formed, and the property of the surfactant is being drastically changed. Okay, what are the properties I'm talking about? First is equivalent conductance. EC. How the equivalent conductivity changes after the CMC is reached. This is EC. Let's second is surface tension. Surface tension before the CMC is decreasing. After CMC, does not change. It remains as such. Osmotic pressure before the CMC it is increasing. After the CMC is reached, it is constant. Turbidity before the this thing CMC is reached, increasing. After that, is increasing further. After CMC reach, increasing further. So this is the variation of property of the surfactant once it's reached the CMC. EC is decreasing very little, then after that one it decreasing more rapidly, but it is not like in a straight line manner, it is a exponentially. The surface tension decreasing linearly before the CMC is reached. After that, it is constant. Osmotic pressure increasing linearly. After CMC is reached, it is constant. Turbidity is increasing, but a very little rate of increment is slow, but after CMC reached, rate of increment is very high. Okay, why this is happening? Why the okay, what is CMC? As I mentioned before, the threshold concentration at which the Michel holds good, or the formation or the Michel forms. Michel formation is occur at the CMC. Michel form করে গেল. Okay, after CMC এবার CMC পরে যদি concentration is go on increasing, what happens? Reverse Michels will be formed. Okay, so CMC at the point when the Michels form. Near CMC, what happens? So let's start with this. So what is that? This is not electrical conductivity. This is equivalent conductivity. Equivalent conductivity. Okay, near CMC কি হয়? Surface is saturated. Near CMC, surface is saturated with the surfactant molecule. Surface is highly saturated by the adsorption of the surfactant molecule, as I mentioned. Okay, ধরো 80টা 100টা surfactant molecule are adding. So surface is saturated with the surfactant molecule. Okay, so যদি সারফেস টেনশন যদি তোমার সারফেসটাই স্যাচুরেটেড হয়ে যায় with the surfactant molecule, so surface tension আর বাড়বে কোত্থেকে? So surface tension ceases to decrease after CMC. Understood? So surface tension আর বাড়ে না, surface tension constant থেকে যায়. So after CMC of the surface tension কমতে থাকে because surface tension কেন কমতে থাকছে? Because it has the urge to take more amount of surface. ওই জন্য সারফেস টেনশন কমতে থাকছে, টেনশন কমছে। আফটার দ্যাট সারফেস টেনশন আর কিন্তু ভাবছো এবার পরে বেশি দিচ্ছি সিএমসি পর বেড়ে যাবে, হবে না, বিকজ সারফেস ইজ স্যাচুরেটেড উইথ দ্য সারফেক্টেন্ট সলিউশন। ওকে, এবার ডিউ টু দ্য এবার যত সারফেক্ট বাড়াচ্ছ, ওকে, কেন কমে যাচ্ছে? এইখান থেকে কেন কমে যাচ্ছে সিএমসি তে? ইসি কেন কমে যাচ্ছে? ডিউ টু দ্য লোয়ার মোবিলিটি অফ দি মিশেল। Due to the lower mobility of the Michel compared to the surfactant, that's why at EC it is decreased from the beginning. because lower mobility of the micelle compared to the equivalent individual surfactant. Due to this lower mobility, the equivalent conductance is decreased at the CMC. Understood? এই জন্য কমে যাচ্ছে। Similar trend is being followed after that, because again the mobility তো আর বেড়ে যাচ্ছে না, CMC এর mobility সবসময় individual surfactant এর থেকে কম, that's why equivalent conductance is being decreasing at CMC because of the lower mobility of the micelles as compared to the individual surfactant. Again slope, osmotic pressure এর slope কেন কমে যাচ্ছে, and but turbidity slope বেড়ে যাচ্ছে। osmotic pressure কমে যাচ্ছে, turbidity slope বেড়ে যাচ্ছে, because why? because the increment in the molecular weight, যত সারফেক্টেন্টের নাম্বার মলিকিউল সারফেক্টেন্ট বাড়াচ্ছে আমার মলিকুলার ওয়েট বেড়ে যাচ্ছে, ইনক্রিমেন্টে তো মলিকুলার ওয়েট বাড়লে টার্বিডিটি বাড়ছে, টার্বিডিটি বেড়ে যাচ্ছে। আফটার সিএমসি হ্যালিস গোল্ড গ্রুপ এর অসমোটিক প্রসারের ক্ষেত্রে সেই একই, হোয়াট দ্য সারফেস টেনশন এন্ড অসমোটিক প্রসার ইজ একদমই রিলেটেড টু ইচ আদার। এই জন্য আফটার সিএমসি ইট সিজেস টু ইনক্রিজ, বাট বিফোর দ্যাট increment due to the osmotic pressure, due to the increment in the molecular weight. These are by this way the properties near the CMC changes. Surfactant property near the CMC যেভাবে changes হয়। Okay, again size and shape of the micelle depend on the properties of the solution. Size and shape of the micelle depends on the properties of the solution, such as the concentration of the electrolyte or pH of the solution. এটা চেঞ্জ করো, সাইজ এন্ড শেপ অফ দ্য মিশেল চেঞ্জ হয়ে যায়, সাইজ অফ দ্য শেপ। ঠিক আছে, the let's say aggregation number of the SDBS is 80, মানে 80টা ইয়ে সারফেক্টেন্ট মলিকিউল আছে 80টা। সো দি SDBS মিশেলে 80টা সারফেক্টেন্ট মলিকিউল আছে, সো ইট ইজ বিং স্যাচুরেটেড উইথ 80 সারফেক্টেন্ট মলিকিউল SDBS মিশেল। এখানে কি হলো, তুমি ধরো সো SDBS মিশেলের মধ্যে তুমি NaCl অ্যাড করলে, অ্যাগ্রিগেশন নাম্বার ফটাক করে বেড়ে 130 হয়ে যাবে। Why? So from 80, if you add a small quantity of electrolyte, aggregation number suddenly jumps from 80 to 130. Why? আগের বারও পড়ালাম, why is it that? Addition of electrolyte, note it down, addition of electrolyte marks the electrostatic repulsion between the ionic head group of the surfactant. ঠিক আছে, addition of electrolyte masks the electrostatic repulsion between the ionic head groups of the surfactant. So electrostatic repulsion টা কমিয়ে দেয় হেড গ্রুপের। ইলেকট্রোস্ট্যাটিক রিপালশন যখনই কমে যায়, সো কি হবে, সো ইট ফেভারস মোর অ্যাবজর্পশন অফ দ্য সারফেক্টেন্ট। যখনই রিপালশন কমে যায়, সো ইট ওয়ান্টস, ওকে আই ক্যান অ্যাবজর্ব মোর সারফেক্টেন্ট, so they can absorb more surfactant because the electrostatic repulsion between the ionic head groups reduced. 80 যখন, তখন আর এর বেশি নিতে পারবে না, because of the electrostatic repulsion between the ionic head groups. যখনই তুমি সারফেক্টেন্ট ইলেকট্রোলাইট অ্যাড করলে, that repulsion between the ionic head group decreases. When this decreases, it can absorb any আরো বেশি surfactant molecule, absorb more amount of surfactant molecule. That's why aggregation number increased. Okay. Increase in pH. কি হলো, সো অ্যাগ্রিগেশন নাম্বার যখনই, এখানে প্রথমের ক্ষেত্রে অ্যাগ্রিগেশন নাম্বার যখনই ইনক্রিজ করছে, রেজাল্টিং ইন ডিক্রিমেন্ট ইন সিএমসি। ওয়ান্স দ্য অ্যাগ্রিগেশন নাম্বার ইজ ইনক্রিজিং, সিএমসি ডিক্রিজ করবে, মিশেল কনসেন্ট্রেশন ডিক্রিজ করবে, রাইট? Critical Michel concentration decreases once the aggregation number is increased. So once you add the electrolyte, the CMC is decreasing. But if you increase the pH of the solution, the CMC gets on increasing. CMC increases. Why is it so? Because higher increase in pH favors the ionization. Okay, so CMC increases. So pH increase করলে CMC increase হবে, but aggregation number increase করলে CMC decrease হবে. Just mind it. Okay, higher the aggregation number, lower the CMC. So that's why the for longer hydrocarbon চেনের ক্ষেত্রে CMC কম, because it is higher the aggregation number. Higher hydrocarbon chain means higher aggregation number, lower the CMC. Lower the CMC means lower the surface wettability. Surface wettability কমে গেলে কি হবে? That's why glycerin soap does not soluble. Wettability কম। আজকে এতটা থাক, আমি পরের দিন প্যাকিং পেরিমিটার থেকে স্টার্ট করব। ওকে,
Okay, sir.
you understood the things? Okay.